So there are some definitions at the beginning of this book. I think we don't have to go through them systematically, but we can just mention them as they come up. So proposition 1 is pretty straightforward. It says, into a given circle to fit a straight line, equal to a given straight line, which is not greater than the diameter of the circle. Proof. So we have a circle. And D, a straight line. Not greater than the diameter. So we have to fit into the circle ABC a straight line, like going from the circumference to the circumference equal to D. So we're going to pick a diameter. Center E, B, C. A will be constructed in a moment. Obviously, if BC is equal to D, then we're done. Otherwise, and we're assuming that D is less than BC, so otherwise if D is less, I mislabeled this, I guess, so E was not the center, apologize. We don't really care about the center, BC is the diameter. So let CE be equal to D, which we can do by some proposition. I forget which one. It's not written down here, but we remember that. Okay, and then problem with my pen. Just a second. Let me see if I can write this way. Let CE be equal to D, and draw a circle with radius. Could you do it, Ken, maybe? My pen's run out of battery,
sure.
perhaps.
Yeah, let me get out of Wolfcam. Circle with... We're using a finger?
My pen, yeah. My mouse, radius. Yeah. Radius EC. Yeah.
Yeah, all right. I'll try to make it neat like you, but
So yeah, we need a circle with radius EC.
So like, let me
centered at C, obviously. Yeah.
So like this.
Yeah.
There you go.
Okay. And then we call the point of intersection A.
One of them.
Yeah. And join AC.
All right. There you go.
And then, although it doesn't look like it, EC and AC are the same length because they're both radii, And by construction, EC was equal to D, so we're done.
Cool. I guess I can write a bit.
Yeah.
So like AC, A since AC and EC are both radii of the new circle of, I guess, the circle centered at C. Let's see. What are we trying? Let me just erase some of this stuff. I think I did that. EC. Then we're done. So yeah, so we're done. Well, this also is equal to D. So we're done. Right. So we want the straight line to be, I guess, what we call a chord, right? Not just any old line inside the circle.
That's right, yeah.
Cool. Awesome. All right. So I think proposition 2 is also pretty simple. We probably have time for 3. But actually, Dan, your pen is not working.
Oh, no, it just ran out of battery, I think, so it should be charged by the time we get to 3. So let's try and make it.
Oh, okay. All right. Well, if not, I'm happy to scribe again. Let me, how do I, wait. Do I have to kick you off?
Oh, I'm attached to speaker, I'm sorry, yeah.
I guess I can't kick you off.
No, that is not a feature.
No. Awesome. Okay, so I'm too far away now. There we go. Okay. So proposition 2 is, let me just write down. Oh, I need to move this window. Proposition 2. Go back a little bit. 4.2. So this is to inscribe a triangle equiangular to a given triangle in a given circle. So this is a new word that we haven't used before, so I'll say a bit about what that means. So to inscribe a triangle, this is belonging to the definitions that Dan was talking about, but we didn't explicitly say what they were. Equiangular to a given triangle. I guess these days we'll say similar, but equiangular is pretty clear what that means. Triangle in a given circle. So to inscribe means we want to draw a triangle inside the circle in such a way that all the vertices are on the circumference of the circle. So, we're given a triangle, so we're just going to draw a triangle here. All right, so we're given a triangle of some shape, right? We're going to call it DEF. We're also given a circle, which I'll draw over here. Oh, Dan, you know what we should have? We should have a circle tool.
Yeah, Billy's been talking about it. So, yeah, I think Billy watches these videos and I think is
right.
cringes every time we try and draw a circle.
Well, actually, maybe it's okay that now sometimes we need wonky circles, right?
That's right, exactly. Yeah, that's our defense.
Actual circle, we may be in trouble. We may have really small details in the diagram that you have to squint to see. Yeah. So this one's our given triangle. Let me just given triangle. Okay, so I kind of neglected to say this. We're going to construct a line which is touching the circle at A. I'll just write that here. Oh, I erased it. Right. Which is touching the circle at A. I'm gonna. This is really the beginning of the proof. But since I'm on this page, I'm going to make some of the constructions here, and then I'll write down what I'm going to do in the next board. Okay, so what we need to do is we need to construct angles that are the same as the triangle, or the same as the angles in the triangle that we're given. So the first line we're going to construct is we're going to construct a tangent line or a line outside the circle that touches the circle at A, and then we're gonna draw a line like this, and this angle is gonna be the same as this one. I'll write down what we're doing a little bit later. As I said, I'm going to repeat the construction for another angle like this, and I'm going to join up these two lines, and then you can probably see where we're going with this, because now we've got almost the triangle constructed with the same angles, but I need to prove it to you that this is actually the case. So B and C. So next board, I'm going to say in words what I was doing over there. So that's the proof. So the proof is that we're going to construct an angle. So construct. Oh yeah, sorry, forgot about that. Is that far enough? I think that's good. Cool. Construct an angle HAC. So this is actually an angle at A. Let me just angle. Oh, sorry, I forgot to label some of the lines. So okay, this line that we've drawn here, we just labeled a point on it. I didn't label the two ends of the line. So let me just put them in so we can refer to the line so you know what points I'm talking about. So the line is GH, touching a circle at A. So A is a point on GH. So in construct an angle on GH, I guess at A, right, equal to DEF. So DEF is an angle in the given triangle. So that's the angle I've marked with one red line, right? So you can see on the diagram. So we're going to do that, and we're going to do this construction also for So construction angle GH at A. I guess the angle will be like HAC. Right, and we're going to repeat this construction respectively GAB. Right, so this is the other angle, respectively DFE. Right, so this is just constructing two of the angles of the triangle along this line. So you get FAB to be equal to, GAB, which is equal to DFE, and HAC to be equal to DF as marked in the diagram. So the proposition from long ago that allows us to do this is proposition 123. This is all the way back from 1. So now, more recently, right, we've had propositions about angles, external angles on these lines and angles in opposite segment of the triangle. So we're going to use that proposition, which is proposition 3.2, to tell us that HAC is equal to the angle in the opposite segment, and that one is ABC. Of course, once we have this conclusion, the same thing applies to the other one as well, right? So I'm just going to write that here, respectively, GAB, right, and it's equal to ACB. So I'm going to go back to the diagram and mark these in there, and then you can see what's going on. So now we've got two of the triangles, two of the angles of the triangle constructed as two of the angles in the triangle inscribed in the circle. And so now, finally, the last angle must be the same, because the angle sum of a triangle is equal to two right angles. So that's proposition 1.32. So by proposition 132, right, the angle sum of a triangle is equal to two right angles. The remaining angles must be the same. Are the same. Same, i.e. BAC is equal to DEF. Not DEF, it's EDF.
Right.
Cool. And that's it. So now we've got a triangle inscribed inside the circle, possibly of a different size, but all the angles are the same.
Yeah, we don't really have a clean way of saying it's the same triangle but scaled up yet, right?
Right.
I guess
equiangular is the shortest way they have now, right?
Well, yeah, we know that's what it's supposed to mean, but I think this operations of inscribing equiangular triangles into a circle where we can control the radius is kind of maybe a indirect way of saying scale up the triangle or something.
Right.
I guess we'll find out. Okay, let's move over here.
Is your pen all right?
Should be, I think. We'll find out.
Wow, it's a quick charge.
Well, it does charge quickly, but I'm not sure if it'll last through the proof. We'll see.
All right. I'm on standby.
Yeah, that's
I'm on standby.
Okay, so proposition 3.3. Yeah, this is really cool. I enjoyed this. About a given circle, to circumscribe, I'll explain what this means. A triangle equiangular with a given triangle. So to circumscribe a rectilineal figure around a circle, if you look in the definitions, means that you draw it such that every line in the figure, in this case the sides of a triangle, touch the circle. Okay, so let ABC be given. Gonna need a fair bit of room. So as usual, ABC are meaningless right now, but will come to mean something in a moment. And DEF, the given triangle. So that's over here somewhere. Okay, so produce EF in both directions. To GH, doesn't really matter how long this is, we'll just make it a little bit longer. Let K be the center. And draw KB at random. Which sounds a bit weird given that we've given B a name already, etc., but you know what I mean, right? So purely geometrically, you just take the circle, you pick the center, then you just draw a radius to wherever and call that wherever B. Alright. A and C don't exist yet, really. Okay, so on the straight line KB, at K, let BKA be constructed, now A exists, equal to DEG. Alright, so that's DEG here, and I guess I should at least vaguely match up the angles. So that's there. And BKC equal to DFH. So that's prop 1.23. BKC. And through ABC, let LAM, MBN, and CL be drawn touching the circle. Now this is it's going to be a cramped figure, I apologize, but we'll make do. So, okay, touching, kind of touching, goes over here. Oh my god, I'm going to have to slice off some bits. Yeah, anybody who can draw that in one go is a genius, in my opinion. Right. So dot 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 dot. So that's L over there somewhere. That's M, and that's N. Okay, so we can draw those lines by one of the propositions we proved in the previous book, and then they meet somewhere. Why do they meet? I guess that's the fifth postulate. I didn't think about it, but yeah, that must work. So you need to think about the fact that there's like an acute angle on one side or something, and then they must meet, and that gives you M, N, and L. But I think there is a secret use of the fifth postulate here, maybe. Let's flag that, maybe. Okay, so now we have our triangle. So since they've been drawn touching the circle, these are all right angles, right? So here, 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 here. So we have right angles at many places. That's proposition 318. So now we focus on some quadrilaterals. So let's look at this one here first. So consider AMBK. Now, the sum of all the angles is 4 right angles, because you can divide the equilateral into 2 triangles, and the sum of angles in a triangle is 2 right angles, right? So the sum of all the angles is 2 right angles, but we know 2 of them, MAK and MBK, are already right angles. So that means that if you take AMB and AKB together, that must be 2 right angles. Okay, so that's kind of neat. But DEG, DEF, let's see, where's, yeah, DEG, DEF are also 2 right angles. I won't cite the proposition, it's just that it's like proposition 1.13, yeah. Okay, so what does that mean? It means that AMB AKB equals DEG DEF. But we knew by construction that AKB equals DEG. So subtracting gives AMB equals DEF. And you can see where this is going, right? So now we've constructed a triangle circumscribing the circle with one of the angles agreeing with our desired triangle. Let me mark it in red perhaps. So this now matches with that. And then you see how it goes. So we do the same thing to the other. So similarly, just at the other vertex, we can prove that MLN, Yeah, so similarly we prove that LNB, that's what I wanted to say, LNB, or LNM, it's the same thing, equals DFE. And so, since they're both triangles, MLN also equals EDF, which is what was to be shown. Yeah, that was fun. I'm looking forward to this book if they're all going to be like this.
Yeah. So next week, I'll start with 4, which is kind of not quite the converse of this, but it's the other construction. You're given a triangle and you want to inscribe a circle inside of it.
Yeah, right. Yeah.
Yeah.
Okay,
cool, man.
thanks again.
Cheers. See you next time.